Okay, we'll be going through the Galaxy Year 2022 Paper 3, which is the practical. So let's start. Okay, so this paper is broken down into 3 main questions. The first one 14 marks. Okay, second question 18 marks. The third question has 8 marks in total, adding up to 40. So let's start at the first question. Okay, so first question starts with you're gonna investigate the reaction, okay, between aqueous sodium carbonate and aqueous barium nitrate. I think as you start experiment, it's always very important to know what's gonna happen. Okay, so question you gotta ask yourself is sodium carbonate plus aqueous barium nitrate. Okay, let me zoom in a little bit. So what exactly is gonna happen here? Okay, I know some of you may not have that kind of theory backing as of now, but those of you who have it, actually it's very important for you to really think through what's exactly gonna happen. So what I have is sodium carbonate, so aqueous, okay, and then aqueous barium nitrate. So let's write out the equation. So sodium carbonate aqueous, okay, barium nitrate aqueous. So question you gotta ask yourself is, okay, when I put these two together, what's exactly gonna happen? Now, you have learned a few types of reaction. One is redox, one is acid-base reactions, combustion, all the various reactions. But if you look exactly at this, okay, now, you know that there's no acid involved, there's no alkali, there's no real alkali involved. It's just, so what you exactly have here is, if you think carefully, it's actually a precipitation reaction. You may not have known it, actually in the midst of it, as you're doing an experiment, you should somewhat be able to see this happening. So in actual fact, when you have these two mixed together, you're going to have barium carbonate, which is the precipitate that you're going to have, plus sodium nitrate. To balance it, two of them. So in actual fact, in this whole experiment later on as we read, okay, you know that in the reaction, you're going to measure how much precipitate is formed. Okay, so this is the experiment here. So first up, they say fill the burette up to 0.00 cm cube mark. So look at this, this is a 2 decimal place, okay, because it is done by burette. Next, we label test tube 1, 2, 3, 4, 5, 6 and place them in order in the test tube rack. Use the measuring cylinder to pour 6.0 cm cube of aqueous barium nitrate. So you realize that aqueous barium nitrate is actually fixed volume. Okay, fixed volume. Then, in each of the test tube, I had 1, 2, 4, 5, 6, 7. Take note, it's 1, 2, then you realize, hey, here got one part missing. Where's my 3.00 cm cube? Okay, so this is the part where you gotta remember that if they have a data like this missing, okay, please make sure that you don't go and do the experiment. Okay, most probably you are gonna have it. They may ask you something about it later on. Okay, so I got 1 cm cube, 2, 4, 5, 6, and 7. Okay, I'm gonna put, after I put the aqueous barium nitrate of 6 cm cube in, so this is my test tube. After I put 6 cm cube of aqueous barium nitrate, I'm going to add in different amount of sodium carbonate. Then they say use the glass rod, stir the contents of each of the test tubes and leave the content of the test tube to stand for at least 10 minutes. Okay, so you leave it there for at least. The word is at least. Okay, so why should you leave this there for 10 minutes? Now, when you add the sodium carbonate in actual fact, after you have added it in, you realize that there will be white precipitate form. Okay, white precipitate form. So, what's happened that the white precipitate is actually floating all over in the test tube. So when you leave it there for 10 minutes, what you're actually hoping is for the whole thing to settle down. You're waiting for the white precipitate to settle down. Okay? Or to sink to the bottom. Okay? Now, why do you want the white precipitate to settle down to sink to the bottom? Because in this experiment, after 10 minutes, you're supposed to use a ruler. Okay, so those of you who say 20 minutes, 30 minutes, okay, actually in actual fact, you're supposed to wait until about 10 minutes. Okay, the longer you wait, actually it may not affect too much. It really depends on how fast your things settle down. Okay, but generally follow the instructions of the experiment. They say after about 10 minutes, use a ruler to measure the height of the solid formed. So, when the thing has settled down, your test tube, this is the solution, you will have the solid compact at the bottom. Okay, this is your white PPT, your white solid. So you're supposed to measure the height over here from the base of the test tube. Now, the measurement of the height is actually quite important. You need to think through how can you measure consistently from the base to the height that you want. Okay? And next thing, you also need to take note, because you are using a ruler you can only measure up to 0.1 cm. Okay, this is the precision of the instrument that you can go for. It is the precision of instrument that they also record to, okay, for the ruler. So what happens is that when you are doing this, okay, you also use a ruler to measure height. Once you have measured all the height, you also present and record your results in a table. Now, so this is a test of your presentation. Okay, presentation of data. So how you go about doing this is actually quite important, because this is a test on your presentation of data. You realize that there will be marks allocated. Okay, there will be marks allocated for how you present. So proper heading, proper units and heading is important. Okay, these are the 3 columns we are looking out for. Okay, so take note, the title, please don't have any short form. So we have test tube number 1 to 6, volume of aqueous sodium carbonate, and the height of the solid. So you realize for this one here, okay, the accuracy we're hoping for it to go up to is not hoping. The accuracy we're looking out for is actually 1 decimal place, okay, in cm. For the volume of aqueous sodium carbonate, we are looking for 2 decimal place in terms of cm cube. Really, why? Because this one we are using burette to measure. This one we are using the ruler to measure. So, how many dPs do you measure to is really depending on the instrument that you're using. Okay, and the last one, the trend of the height of the solid. In actual fact, as you're measuring the height of the solid, you should see that when the volume of sodium carbonate, okay, gets more and more, the height of the solid should actually get more and more. By this, you actually realize that sodium carbonate is the limiting reagent, because the more you add, okay, the more solid you get. Okay, this solid you're actually getting is your barium carbonate. So if sodium carbonate is the limiting reagent, it also tells you that your barium nitrate is your excess reagent. So as you're doing the experiment, all these things should be running through your mind. You should be thinking what's really happening. Don't just leave it. Okay, I say again, don't just leave it. Okay, as it is, you just do. It's not really about just doing. You really must think through what you're actually exactly doing. So the table itself, the presentation of data, is what we're looking out for. How you record it to. Record it to is really about how you actually measure your data. Okay, how you record it to. How much you record it to. So just take note of this. So once you're done with this, actually the 4 marks, this is the allocation of it. Then we go on to plot your graph. Okay, plot your graph. Now, in the midst of plotting the graph, this is the marking scheme actually we're looking out for. The best fit start from 0. And I think some of you are asking, Cher, why must I start from 0? Okay, is it always important to start from 0? Now, I just need you to think through this experiment. If you didn't add any sodium carbonate, if there's 0 cm cube of Na2CO3, 0, what do you think will be the height of the solid? How many cm will be the height? So, whether to start from 0 or not really depends on your experiment itself. Okay, it really depends on your experiment itself. I think when we compare physics and chem, I think physics, sometimes the y-intercept has a separate meaning. Okay, and if you know what the experiment is about, you know what's the meaning of the y-intercept, then it actually helps you to understand, should I start from 0 or not. In this case here, if I didn't add any sodium carbonate, I will have 0 products formed, and hence the height at which I'm starting should also be 0. Okay, 0.0. Okay, let's be more precise with whatever I'm writing. So if I had 0.00 cm cube of sodium carbonate, which is no sodium carbonate, I will have 0 cm height of solid form. Okay, so just take note, that's why it must start from 0. And the line of best fit, if you look at this, you say, hey, Cher, this one don't look very best fit. Why doesn't it look very best fit? Actually, it does. How do you go about actually doing best fit? So let me use different colors to illustrate for you. Okay, so really it's about having the least amount of distance from the line to the points and making sure that the distance above and the distance below are the same. What do I mean by that? Okay, so let's use this example. Let's look at this point over here. Okay, let me show you this distance here is somewhat equals to this distance here. So you can see for this point, let's call it point 1. Okay, it is counted. Okay, maybe this color too hard for you to see. Let's use a darker green. Okay, let's say this is point 1A. Point 1A is counted by point 1B. Okay, because you can see the distance here. So I compensate. So for point 1A, you realize the distance of it away from the graph, okay, above the graph, right, it's actually compensated by the distance of which point 1B is away from the graph. Okay, next. How about this? Say, Cher, this one, let's call this point 2A. Point 2 above the graph is compensated by this one, point 2B, point 2 below the graph. And the last one, you can see here, point 3. These two are somewhat equal, point 3A, point 3B. So realize to draw the line of best fit, we are looking at the distance of the point away from the graph, okay? So the amount of distance that's above the graph from the point, okay, from the line to the point, okay, this distance over here should be compensated out on the top and at the bottom. So that's how we go about drawing the line of best fit. Okay, so as you can see here, I think you should have a better understanding now of how to draw the line of best fit. Secondly, is all points plotted correctly. Okay, so the teachers will literally go in and they will check at this point, is it plotted correctly or not. And when we say plotted correctly, what are we really looking out for is that the points are plotted to accurate, up to half of the smallest division. Okay, half of the smallest division. So in this case here, if you look at the graph that we have here, the smallest division would be like this part over here. This part is actually 0.2. Okay, this division over here is 0.2. So what is half of the smallest division? It's actually 0.1. So we'd expect, so 0.2 is the half of the smallest, is the smallest division. Okay, why I divide by 2? Because I want half of the smallest division, and hence I can record up to 0.1. Okay, record up to 0.1. So all the points are plotted accurately up to half of the smallest division. Okay, so these are all plotted to half of the smallest division, accurate up to half of the smallest division. Okay. Then the last one is the plotted points fit 3/4 of the graph. Actually, one other way to go about gauging this, how do I know whether it has is more than 3/4 of the graph? Okay, one of the other ways to look at it is, let me use a different color now. Maybe I use pink. Okay, so in terms of x-axis, so this one, in terms of x-axis, so this is my lowest x-axis value based on the plotted graph. This is my maximum. Okay, this distance here should take up at least 50% of the x-axis. Okay, next thing, from here all the way to the top here. Okay, so you look at the y value of the smallest point to the bigger, from one end of the point to the other end of the point. So you realize this is the y-axis value. This should also be at least 50% of the graph. Okay, so to gauge whether it fits 3/4 of the graph paper. Actually, that sometimes it can be a bit difficult. So one way you can look at is using the y value, okay, to see whether does it take up at least 50%, to see whether does it take up at least 50%, okay, from the y and the x-axis side. Okay, so that's how you can go about gauging on this one here. Now, of course, the marking scheme may differ slightly from point to point. So what should I really be looking out for whenever I plot my graph? Actually, the key 4 points that you should always look out for is S, L, A, P. You wouldn't go wrong if you go about this. So what exactly is S, L, A, P? Sorry, maybe I shouldn't write in this manner. I should write like this. S, L, A, P. So we're looking out for the scale. So the scale is really about the 50% thingy. Okay. And please make sure that you use a good scale. Normally, every 10 small squares, it will be in multiples of 1, 2, 5, and 10. Okay, please don't give us odd scales as much as possible. Okay, second thing, we look out for the line. So the line is really about the best fit. Okay, best fit line. Next is axis, whether you have done your axis accurately and properly. Okay, with the label of the axis drawn carefully. Every 10 small squares, go and label. Okay, make sure you have make sure you label your x and the y value at the starting point, both of them. Okay, things like this. And the last one is your plot. Okay, make sure that you have plotted all your points accurately. So if you have thought through SLAP for your graph, you shouldn't have too much mistakes in your graph. Okay, at least you have considered most of the points, or actually all of the points that you need to do. Okay, so that is for your graph side. Okay, so this is the data that we have. Now, part C. From the graph, deduce the height of the solid form when 3 cm cube of aqueous sodium carbonate is added to 6 cm cube of barium nitrate. So some of you may ask, hey Churcher, where is this 6 cm cube from? So you go back to the very original part, okay, when you read, okay, not original part, but the very starting part, you realize all of the test tube 1 to 6, the amount of barium nitrate added is fixed 6 cm cube. So, in actual fact, when they say that when 6 cm cube of aqueous barium nitrate is added, they're just saying, okay, with the same condition of the starting condition, okay, now I want you to find for me when 3 cm cube of aqueous sodium carbonate is added, what exactly am I gonna get in terms of the height? So this is where you go back. Because they want from the graph, you need to indicate. Okay, how exactly do you indicate? So this is where 3.0 is. Okay, so my suggestion is write the 3.0 there. You're supposed to do the dotted. Dot, 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 dot. Please use a ruler. Until this point. Okay, then you dot. Oh no. Okay, please go and dot accurately. Okay, go and dot all the way to here. And then you will go about labeling. So this will be 5.4. This will be the height. So then the answer here will be 5.4 cm. So shown on the graph, please must show using dotted line. The accuracy of the results must be shown to half of the smallest square. And please take note, you should have your units there. So the word cm is important. Some people have left out cm because they just thought, yeah, I got my value and that's it. But take note, all of your measurement here actually has a unit cm. Because it makes a difference. 5.4 can be meters, can be millimeters, can be cm. So which one is it? Okay, so it's very important to include your units. All your physical quantities, things that you measured, must have a value itself and have a unit. So just take note of that. Okay, next part D, describe. So there's two things, describe and explain. Okay, a lot of people are able to describe the trend because after they draw it out, they can describe the trend. But the explanation part is the thing that's missing in many of your descriptions. You didn't explain the trend itself. So most of you are able to say from test tube 1 and 2, okay, or from test tube 1 to 6, when the volume of aqueous sodium carbonate increases, the height of the solid or precipitate increases. Now, if you want to be even more precise, what you could actually say is, based on this, okay, as the volume of sodium carbonate increases, so maybe I can start from my graph, because this is the trend is generally from a graph, right? In actual fact, you should be using data from a graph. So, when sodium carbonate is 1.0, actually my reading here will be, this is actually a 1.0, 1.9. Maybe I'll use another point here. Maybe let's use this point over here. Okay, never mind, don't use that point. The point not very nice. Let's use a nicer point. Let's use this one. Okay, let's use this one over here. This one is sodium carbonate 6.0. Okay, then the height of the solid will actually be 10.7. So what I will most probably say is when the volume of aqueous sodium carbonate increases from 1.0 cm cube, 1.00 cm cube to 6.00 cm cube, okay, based on your graph, okay, the height of the solid or precipitate increases from, in this case, my graph would be 1.9 to 10.7. Sorry, 1.9 cm to 10.7 cm. Okay, and all of this is actually based on the graph drawn. Or you can say from the graph. Okay, from the graph. So the question is, why is it that when the sodium carbonate increases, the height of the solid or the height of the precipitate increases? Okay, the key idea here is because the sodium carbonate is the limiting reagent. Okay, I would say that some of you have actually explained that because it's the limiting reagent, as I increase the sodium carbonate, more and more of the barium carbonate is formed, or more and more of the product is formed, or more and more of the precipitate is formed. So the explanation part is the one that is missing here. So take note, always underline what, or you go and circle the words, okay, in the question that tells you what are the parts you must answer. Okay, please don't miss out, especially when you talk about explanation. Okay, if for those of you who think that, sure, have I really explained? Have I really done what I need to do? So question is it sufficient in what I've written? Simple. When you see explain, okay, whatever you have written already, let's say for example, whatever you have written already, okay, whatever you've written already, because of the word explain, right, I want you to ask yourself why one more time. So for example, in test tube 1 to 6, when the volume of sodium carbonate increases, the height of the solid and precipitate increases. Okay? Because you see the word explain, you ask yourself why. Then you, as you write your next sentence, make sure that it must explain the trend. That's why the word why actually is sort of like to help you to explain. If you kiasu, you see one time explain, maybe you want to ask yourself 2 times why. Why? After you write your sodium carbonate is a limiting reactant. Why? Okay, so you can ask yourself why to see whether your answer is complete or not. 1 explain actually equals to 1 why. Okay, but if you want to kiasu a bit, you can ask yourself 2 times why. Okay, if you're able to answer 2 times why, actually you're more or less quite there, because each time I ask why, you're actually going deeper into the knowledge that's required. Okay, next, describe the steps used to prepare a pure sample of the solid produced. So in actual fact, when you react, you already have the solution with the solid over here. So this solid that's being produced, we are looking out for is this one over here, okay, which is your barium carbonate. Okay, some of you went to redo the whole experiment. Some of you thought the solid produced is some other solid. I do not know why, okay, but if you have been following through the experiment, you know that the solid produced is the barium carbonate. You already have it in the test tube. So what should I do to get the solid out? The thing is, describe the steps. Okay, describe. So you must make sure that you write it out properly. Don't just write down the process. So some of you just write filtration. After filtration, you're going to tell me wash and dry. In actual fact, you must describe what's happening. So first thing that you do is actually to filter the mixture. Now, why you want to filter the mixture is actually to collect the residue or collect the solid. So don't just filter. You must tell me what you are collecting. Second thing, once you've got the residue, you need to be able to wash and dry it, right? Why you want to rinse it with some cold distilled water is really because you want to wash away impurity. Okay, then this one obviously is to dry it. So rinse and then to dry. Okay, many of you say the filter part, but you forget to rinse and you dry. Or you rinse, never dry. Or you dry, never rinse. Okay, so the rinse and the dry normally comes together. If you remember all your salt prep method, at the very end, there's always the step where you need to rinse with some cold distilled water and to dry it with filter paper. Okay, so take note. So the described step part, generally, most of you know what's happening. However, because of the word describe the steps, well, a lot of you just, okay, let's just say you missed out some part. Maybe theory part you never cover too much, but I thought it's quite common sense. If you have done enough, if you remembered enough, actually this one should come quite easily. That's if you understand the experiment. Okay, last one, suggest why the contents in the test tube were left to stand for 10 minutes after. Suggest why, why actually this explanation. You got to suggest. So this is like to think through and then provide an explanation for it. So why were they left to stand for 10 minutes? Left to stand for 10 minutes after the aqueous sodium carbonate has been added to barium nitrate. So they want to include equation. So equation here, because there's only one balanced chemical equation, actually you don't need state symbol. Okay, normally if they want state symbol, when would you need to write? When you need to write is, first thing when you see ionic. Ionic confirm need state symbol one. Second one is when they say with state symbol. So in this case here, because they only want a balanced chemical equation, in actual fact, you don't need to write state symbols there. Okay? But with the state symbols, actually it helps. As what I did just now at the top there, you realize that these two you're adding at the start is aqueous. Sodium nitrate, all nitrates, all sodium salts are aqueous. So that's soluble. That's why this will be aqueous. Barium carbonate is actually a solid. So in actual fact, you are having barium carbonate as a white solid, as I mentioned. So when it precipitates, it's actually all over in the solution. So what I need to do is, I need it to settle. Now, it's not just good enough to say that you need it to settle. Why you want it to settle? It's really because you want to ensure that you have a accurate, actually if you ask me, I'll use the word accurate results. Okay? What is this accurate results referring to? Actually, is when you're measuring the height of the precipitate form. Imagine they settle at different juncture. Some settled more, some settled less. The height of the solid form will be different. Okay, the height of the solid form will be different. Therefore, it's important to make sure that the precipitate has sufficiently settled so they can get an accurate result. Okay, so they can get an accurate result. Okay, so whenever you're measuring the height of the precipitate form. So thinking through the experiment is really important, okay? So those of you who never really think through the experiment, you realize, no wonder I don't understand what's happening. I'm just like, oh my gosh, I'm lost. Okay, some of you thought, okay, some of you in the midst of experiment, you're thinking, why the graph cannot be a V shape? Why the graph cannot be a V shape? Because maybe some of you say, my graph looks like this. Okay, and actually this is quite possible, right? Maybe at the start here, my sodium carbonate is limiting reagent. At this point here, my barium nitrate is limiting. No problem. It's possible to have such a graph. But, you look at this. Draw a line of best fit. So typically it's just one straight line. You won't have a V-shaped graph. In order to do the V-shaped graph, actually what you will have in the instructions is that they will actually tell you to draw a line from don't know where to where. Okay, may draw a best fit line. Draw a best fit line. Then after that, they'll tell you draw another best fit line from where to where. Okay? So you say, can it be a curve or not? Can it be a curve? If you know the reaction, you know that as you add more and more products, okay, actually it's proportional. Why? When I add more sodium carbonate, the amount of barium carbonate increase should be about proportional. Okay, therefore it cannot be a curve as well. So realize by knowing the concept, the theory, okay, behind what you're doing, why you're doing certain things, actually it will eliminate that it cannot be a curve for this, cannot be a curve. Okay, and if you're thinking through, you also know that because of the instructions, you know that it cannot be a V shape, no V shape. Okay, or you want to think of carrot shape, whatever lah. So all of these are actually clues, okay? And that's why it's important whenever you are doing such experiment, okay, when you do a practical, it's not just purely doing. You need to be able to understand what's happening at the background. Okay, so this one is for the first experiment, 14 marks. Second one, okay, this one is the one where a lot of people really don't know what's happening, but actually explanation is quite clear. Let me tell you what's exactly happening. So a student investigated the redox reaction between potassium iodate 5, what the crap this is, many of you do not know, right? But in actual fact, it's here. So it's actually KiO3 and iodide ions. Iodide ions, I minus. Okay, so what do I have here? I got sodium thiosulfate, which is called solution A. I don't know what thiosulfate is yet, but if I read later on, you'll find out. Solution B, I got 0.0 of potassium iodate 5, and then P is a dilute acid. I do not know what is P exactly, but I know if it's acid, it contains H plus ions. Okay, because why definition of acid is when dissolved in water, it must produce H plus ions. Okay, next, fill the burette with solution A. So thiosulfate goes into the burette. So these are little things that you should be annotating. Oops, actually I spelled burette wrong again. Oops, sorry. Let me go and spell. No, actually spell correctly. So burette. It just looks weird to me suddenly. Okay, never mind. So burette, you put this in the burette. Okay. Next, using a measuring cylinder, transfer 10 cm³ of solution B. So I'm going to put in the conical flask. Okay, my conical flask. I'm going to put 10 cm³. Don't just write solution B. Take note of what it is. So I'm going to put KiO3 inside there. 10 cm³ of KiO3. Okay. Next thing I'm going to throw inside, add another 10 cm³ of unknown dilute acid. So I'm going to throw another 10 cm³ of acid. So 10 cm³ of H plus. And then followed by 20 cm³ of potassium iodide. So I'm going to throw in 20 cm³ of Ki, potassium iodide. So these are the three things I've added in. And realize, hey, isn't this like the three things I added? So this equation represents the reaction. So this equation here that you have, equation 1. So let's call this equation 1. This is actually the reaction between potassium iodate 5 and your I minus, which is your iodide ions, which is present in Ki. So these two are the things that's really reacting. Your acid actually just produces the H plus for the reaction to happen. Okay, so in actual fact, when the potassium iodate 5 reacts with the iodide ion, you got a few products. One is you get the iodine. This iodine, this is not iodide. Then you got potassium sulfate and you got water. Potassium sulfate is a salt that's produced from the reaction. Okay, then followed by water. After that, solution A was added to the flask until the content turns pale yellow. So the question is, solution A. What's my solution A? Sodium thiosulfate. S2O3 2 minus. This one confirm not sodium, right? So what exactly is S2O3 2 minus? This is actually your thiosulfate ion. This is your thiosulfate ion. So in actual fact, sodium thiosulfate is actually Na2 S2O3. Thiosulfate S2O3 is an ion. Okay, it's an ion. When you add A in, it actually reacts with iodine. Then the question is, I thought only iodide and iodate 5. So where exactly did the iodine come from? So the iodine is actually from here. You see? The product from the reaction of iodate and potassium iodide produces iodine, which is then fed into here to react with your thiosulfate. Right, so the thiosulfate is actually there to find out. So what exactly am I doing here? If you think about it, I'm doing titration here, right? So titration is between thiosulfate and iodine. So if I'm titrating using my thiosulfate, most probably I'm trying to find how much I2 is in the solution. Okay? In the solution, meaning that how much I2 is produced from the reaction. So this is the concept behind whatever that's happening here. Okay, but I know the reaction looks weird, and hence it's like, oh no, actually what exactly is happening? So step by step, take it step by step. So I know this, the reaction is happening. Iodine produced is now titrated against my thiosulfate. Okay, they actually tells you what's exactly happening. You add it slowly to the flask until the content turns pale yellow. Okay, I may not know what exactly is this whole reaction that's happening. Why does it turn pale yellow? Never mind. Just take it as this is some of the steps that you must be observing. So burette reading starts here. So this is my initial burette reading. Burette reading. Okay, which should be my 0.00 cm cube. Okay, when I start adding in, that's the start. Add pale yellow. Okay, once it turns pale yellow, add 5 drops of starch. What is supposed to happen is that it's supposed to, the solution, the color of the solution will turn to blue-black. So pale yellow to blue-black. So solution turns from pale yellow to blue-black. Pale yellow to blue-black. Why should I do this? Never mind. Okay, we may not know, but at least think through the experiment first. Turn pale yellow to blue-black. Okay. After that, swirl the flask and then continue. Why must you swirl? It's just to make sure that this is to make sure that the starch is mixed well, okay, into the solution. Okay, so that your whole thing actually reacts. Okay, then continue add solution until the blue-black just disappears to form a colorless solution. So what I'm looking out for is when the blue-black becomes, so what I'm looking out for over here is blue-black becomes colorless. So when do you stop adding sodium thiosulfate? When do you stop adding it? It's when the solution turns colorless. So my final burette reading will be here. Okay, so you know that whenever you're doing your titration, there's always the final burette reading and the initial burette reading. So to know when you should write down your final burette reading, actually it's like that. Or typically, when you do a titration, there's no intermediate burette reading. There's only the initial and final. Okay, so this is what is happening here. Okay, I've already run through roughly what's happening here. Okay, making sense of the two equations. So let's start, okay, on really looking at how to go about getting your things. So record your titration results in an appropriate format in the space provided below. Okay, space provided. So this is really looking out for how you present your data again. So those of you who think presentation of data is not important, I'm sorry, it is important. Okay, and to know how to present your data, it's not just about drawing the tables. You need to know what exactly I should be doing. Okay, how to exactly present my data. So for titration itself, actually there's a very fixed table format. Okay. Next, they say also repeat the titration as many times as you consider necessary to achieve consistent result. Now, when we're looking at a consistent result, we're looking at your titration, okay, your titration results, okay, your burette reading, okay, the volume added, right, should be your titer, okay, I don't call it, the results are, okay, your, between your different titrations, okay, your two best titration results, actually not should, it must be, okay, when you want consistent result, must be within 0.20 cm cube from each other. So we're looking out for really 0.20. Of course, you can 0.10 or exact, it'll be best lah. But if cannot, actually the key here is they must be 0.20 from each other. So let's look at the results that we have over here. So this is the table I'm looking at. So typically you have your what we call the titration number. Take note, it's not limited to 1, 2, 3. You can have 4, you can have 5, you can have 6, depending on how many times you have done it. You should have your final burette reading. Please take note of the header, final burette reading. You have your initial burette reading. So final, then initial first. Why? Because when you want to find the volume of solution A used, it's actually taking the final, subtracting from the initial to get your volume of solution A used. So you can see here why we have the final burette reading first, then the initial. Okay, so you subtract them off to get it. Then last row at the bottom is to indicate which is your best titration results. So it's not looking for one, we're actually looking at the best two. Okay, to take together to form your to show your consistency. Okay, so this is the table I'm looking at. You can just memorize this whole table here. The only thing maybe you need to change is this one here. Okay, volume of something can be sodium hydroxide. So volume of solution P, solution Q. So just volume of whatever that's being used. This volume of whatever that's being used is whatever that's pumped into your burette. Okay, so this table is important. If you look at the thing here, okay, presentation, we give you 2 marks. 1 mark if the values recorded follow the accuracy of the apparatus. In this case here, because it's burette, we should read it up to 2 decimal place. And it should be 0.05 cm3. Please don't give me what, a 26.21. How the crap do you actually read this 1 over here? Rubbish. Okay, please don't anyhow. So it should be 2 decimal place, and it should be either a 0 or a 5 at the second decimal place. Next one, make sure 1 mark for the correct heading, so titration number, initial burette reading, blah 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 blah, together with the correct units also. Okay, so presentation, 2 marks. 1 is for the reading of the burette to 2 decimal place. The other one is making sure that all your necessary headers are present. Okay, take note, this units here is actually a /cm3. So some of you don't want like that, you want to like that, also can. Okay, like that also can. So just take note, your units are equally as important, okay, whenever you are doing the table. Next one, accuracy. So this is the one where you're not so sure, okay, how do I know how accurate my results is? This one you won't know one. That's why you just have to do, and then do properly to the best of your ability. Okay? The supervisor will also be doing to the best of their ability so that it will be as accurate as possible, so they can match yours. So typically, this is the part where your accuracy comes in, okay, your experiment, how accurate it is. So if it is within 0.20 of the supervisor, okay, there will be a person in the lab doing it, you get your full 2 marks. 0.3, just slightly above only, you get 1 mark. But with 0 marks, if you got more than 0.3 cm3 away, that means your experiment is not accurate at all already. Okay, so just take note of that. Next one, concordance is really looking at your consistency of your results. So when you say I pick the consistent results, okay, when I pick consistent results, right, they should be within 0.20 from each other. So you can see here, this 2 is within 0.20 cm3 from each other. Okay, sorry, my handwriting. Right, yeah. Okay. So 1 mark if the within 0.30, which this one, I think you can roughly get the idea lah. So within 0.20, 0.30, but in actual fact, actually within 0.20 is the one that we're looking out for lah. So try not to go beyond this. Okay. So this one I think just take note, concordance is actually about your consistency of your titration value chosen. Okay, so this is regarding your titration table that you have over here. And then, now is the theory part. So suggest why starch solution was added. So look back here. Okay, look back at the whole thing here. When you add starch, what's happening before and what happens after? So starch actually causes the solution to turn from pale yellow to blue-black. Pale yellow, blue-black. But is it my endpoint of my solution? Is it the endpoint of my titration yet? Not yet. Okay, so in actual fact, when you think through when I initially started off, it wasn't pale yellow. It was like yellow solution. Then slowly as I added thiosulfate, it turns from, so initially it's sort of like yellow solution. Then it turns to pale yellow. If I don't add starch, most probably I'm still looking out for a colorless solution. Okay, this will actually still be the endpoint, right? This will still be the endpoint. However, from pale yellow to colorless, it is very difficult to determine. So what is happening here is that instead of doing like this, I actually add starch. Once I see it's pale yellow, then it's gonna turn dark blue. Okay? Or it's gonna turn blue-black, blue-black. This color is intense, okay? Or I should say it is easy to see. Okay, it's more visible compared to pale yellow, right? And when I reach the endpoint, you realize it's a very sharp difference from the dark blue, it suddenly will just turn colorless. So this color change is very visible. So why am I exactly going through this whole color change and what exactly is happening here is really because when you add a starch solution, it's really to show clearly the endpoint of the reaction. Why? Because the color change is actually more visible. More visible. Okay? Or you say giving a more intense color change is also okay. So I want to see clearly the endpoint. So you realize that there's the word Y here. Whenever you got Y, you need to ask them. So some of you will just say, ta-da, 1 mark. That is 1 mark, exactly. So if I can see it more clearly, good. But the question is, why do I exactly need to see it more clearly? Why? In actual fact, when the reaction proceeds, the iodine concentration gets lower and the solution colors become lighter. As it gets lighter and lighter and lighter, it's actually very hard to determine the endpoint. Very hard, very difficult to determine endpoint. So, by adding starch, actually we reduce the error to determine the endpoint. Okay, so please don't just say that it's the color, it makes the color change more obvious, more visible. But really, why do you want to make the color change more visible? Is the initial color change not visible at all? Is the initial color change good enough? Obviously, it's not good enough lah. That's why you add the starch. So the word why here tells you that, hey, please have one more layer of explanation. Okay, the word why is the one that's killing many of you. You are not answering to the point. You just think that my one-liner or a little bit of liner is going to help me. So look at your answer and always ask yourself, why? Am I answering the why segment? That's the part I think you all need to work on it. Okay, use your titration value. Use your titration results to obtain the average volume of A used. Show clearly how you obtain this volume. Okay, when you say show clearly how you obtain from this volume, is actually your tick on the boxes here. So what you should have is, okay, average. Okay, let's spell it out. Later, can ask scolded. Average volume of A used is equals to, I'm going to take my two readings up here, 26.40, 26.20, 26.40 plus 26.20, and then divide by 2, I get 26.30 cm cube. 26.30 cm cube. So please take note, it should be to 2 decimal place and to the units, because when you take the average of the volume of A required, actually it's still sort of like you must follow the same accuracy as your result. So therefore 2 decimal place. Okay, so for burette, just put it 2 decimal place, keep it simple. Okay, so that's the average volume, and some of you actually forgot your units. Please tolong a physical quantity, you need both your values, your numerical magnitude, and your units itself. So please. Okay, now A is, they already tell you it's sodium thiosulfate. Using the results from B, calculate the concentration of iodine in 40 cm cube of the reacting mixture. So I need to refer back to this equation over here. Okay, so I need to refer back to this. I use pink, and I will write so many places here. So pink color. So this is the thing that's happening in my titration. I'm using the sodium thiosulfate to react with the iodine. I'm using the thiosulfate to react with iodine. My burette is filled with the thiosulfate. So let's find the number of moles of A, which is the number of moles of thiosulfate. This is the mole of thiosulfate. So I know the concentration is 0.10. Okay. So what I take was the volume divided by 1000. So this is actually to convert to dm cube. Then I multiplied by the concentration to find the number of moles. Okay, to find the number of moles. So W1 is the mole of thiosulfate. So this is the mole of thiosulfate. I'm just going to write S2O3 2 minus. Okay, so this is thiosulfate. So subsequently, I'm just going to write S2O3 2 minus. So based on the equation, you know that actually you don't really need to write the sodium in. You can actually just use the equation that's in your paper over here. Okay, use this over here. So you know that it is your S2O32 minus reacting with your I2 is going to give me S4O6 2 minus plus I minus 2 of them. Okay, and then 2 over here. So you know that the ratio between the thiosulfate and the iodine, this is iodine, so it's I2. Many of you thought iodine is iodide. Please know the difference. Iodine is I2. Iodide is I minus. Okay, so be very clear about it. So I know the ratio will be 2 is to 1. So whatever mole that I have here, this is the mole of thiosulfate, right? I need to divide by 2. So this is actually W1 divided by 2. Okay, this is the mole of iodine. Now I got the mole of iodine ready. What I'm going to take is, I'm going to take the mole of iodine, divide by 40 over 1000. This is actually converting 40 cm cube to 0.040 dm cube. So I'm converting the cm cube to dm cube. So when I take the mole divided by the dm cube here, I'll get the concentration. Okay, so the concentration here, whatever answer. So this is actually a ECF. So whatever answer you have from part B, we're actually ECF here into part C. Okay, that's why you realize we are using W and A instead of a fixed number, because it all depends on your result. Okay, so knowing the reaction, you realize it's going to help you. It's going to help you to know what exactly to do for the calculation. And then with your part C answer, that's where we lead into part D. Okay, so find the mass of iodine. So the mass of I2 present in 2 dm cube of iodine. So first thing, this concentration here that I have is actually mole per 1 dm cube. So actually this concentration is how many mole in 1 dm cube. That's actually what the concentration means, right? So if I got 2 dm cube, first thing I find number of moles here. So it's actually whatever I have up there, I times 2. So this number of mole in 2 dm cube. So this is actually a mole of I2 in 2 dm cube. Once I know the number of moles of I2 in 2 dm cube, I need to find the mass. So this, what I'm doing here is to find the mass. I take the mole multiplied by the relative molecular mass of iodine. Iodine is I2. So you multiply by 254. Okay, many of you just times I because you thought your iodine is your iodide, and hence you just use 127 instead of 254. 254 is actually I2. I2 is actually 127 times 2. This is actually the relative atomic mass of I. Okay, so that's how you get your 254. So 1 mark for the final answer, 1 mark that it should be written to 3SF. Okay, so I say again, this is actually ECF from the top. So whatever value that you got from the top here, you can work it out to the bottom. Okay, so if you left any blank because you thought my initial calculation wrong, I don't know how to do already. Okay, initial calculation wrong, you scared you get wrong for next part. Don't worry, there's always this ECF element that's coming in. So make sure you complete your paper. Don't leave any blanks. You're just losing marks. Okay, which is not right lah. You can get the marks on because of the ECF available in the paper itself. Okay, next. Suggest I explain how the results and the rate of reaction will be affected by an increase in the concentration of Ki. So where exactly did the Ki come from? That's what you should be asking yourself. And when I scroll back up, where exactly did I add Ki? It's at the very initial, at the very start. Ki is added here. So Ki is added at the very start of the reaction. Okay? Now, I'm going to increase the concentration of Ki. Okay, let's assume same volume. So when I say increase the concentration, right? But let's assume, you must make assumption, assume same volume of Ki. Okay, so if I assume the same volume of Ki, actually concentration will affect two things. One is the speed of reaction, because concentration affects speed of reaction. Second thing is because if I have the same volume but increased concentration, I actually have more moles of Ki. Now, more moles of Ki doesn't mean my result will be different. Okay, it doesn't mean that I maybe have more products. It really depends on, you got to ask yourself the next question is, Ki, is it excess or limiting? The thing is that if you read the whole question, they didn't really say. So we're actually accepting two possible results here. It's actually for you all to think through what's actually happening. So if you deem that Ki is an excess reagent, okay, when concentration of Ki increase, actually the same amount of iodine will be produced because I didn't change the limiting amount of reagent, right? So the amount of sodium thiosulfate used during titration will be the same. So this will lead to this. That's if Ki is excess. Because Ki, when it's the excess, it really doesn't affect the final product form. Okay, the amount of product form is limited by the limiting reagent. But let's say I say Ki is the limiting reagent in this case here. If it is the limiting reagent, because now I have more Ki in the solution itself, there will be higher amount of iodine produced. And because there's more iodine produced, the amount of thiosulfate used will actually be more. So the reasoning is important. Okay, so whether it's excess or limiting, it will affect the product formed accordingly. So if it's excess, results consistent, same results. If the Ki is limiting, then I'll have more product. So just take note of that. Then the rate of reaction definitely will increase because concentration, right? But rate of reaction doesn't affect product, so think it just react faster. So if there's a higher concentration, there'll be more particles present per unit volume. So you realize, this one isn't it like my rate of reaction explanation answer is? Yes. So this one is your first 1 mark. Okay, really explaining what exactly higher concentration means. Secondly is we are looking at is the higher frequency of effective collision. The word frequency important. Don't just tell me more effective collision. Don't just tell me higher effective collision. No, the word frequency is important. So you tell me higher frequency of effective collision or higher rate of effective collision, then I'll give it to you. Because you need to include the idea of time. Frequency and rate has the idea of time present. Okay, so this part here, just take note of the answers. Next one, F, thiosulfate can react with acid to form sulfur, sulfur dioxide, and water. Because you do not know what acid is present, okay, in actual fact, the reaction is not very difficult. This is the reactant. This is the product. So what you should do first at the start is just write down exactly what the reaction tells you. So I have S2O3 2- thiosulfate. It can react with the acid. Okay. Because why is it ionic equation? It's because you are using ions. Okay. It's already simplified for you already. I'm going to get sulfur. Sulfur itself, okay, can be quite new to many of you, but actually sulfur is a solid. Okay. S. Next thing, sulfur dioxide, I think most of you would have known by this. This will be a gas that's produced. And last one, water, most of you would know is liquid. So this is the question mark that many of you do not know, right? Okay, let's say assuming you get it correct. Once you have written all this down, then you ask yourself, is it balanced or not? Let's balance start aside. 2 sulfur, 2 sulfur. Oxygen, I got 3. 2 oxygen here, 1 oxygen here. Then after that, hydrogen. Only got 1 here, but I got 2 hydrogen here, so I just put 2 here. Okay, then this is actually balanced. Then you say, the charge like balanced. No, the charge is balanced. Because why? Can you see this is a 2- here? This is a 2 times plus. So actually overall charge on the left is 0. Right hand side, overall also the 0 charge. So therefore, for part F part 1, the ionic equation is actually quite simple. Okay, because you don't need to think too much. You just look at whatever that's given to you, write it down. Then after that, you go and figure it out in terms of balancing. What's the difficult part about this is that you're dealing with thiosulfate that you don't know. You think about acid. Actually, what acid am I using? So some parts, the details are not given to you. You need to make an assumption. Okay, like acid, I know it's using H+ and stuff like this. Okay, so F part 1, quite badly done, at least I would say. Okay, because many of you are unable to either get the sulfur as S, okay, or you just do not know how to start the equation. Okay, but in actual fact, it's given here already, so just take note. Okay, then part 2. A student repeated experiment accidentally used a conical flask that once contained sodium thiosulfate to contain the reaction. So now, I starting got some extra thiosulfate. Okay? Describe and explain the effect it will have on the calculated number of moles of potassium iodate 5. Okay, that reacted with potassium iodide. So how exactly did the thiosulfate? So the S2O32- affects my I2 calculated. So if then this I2 calculated will tell me how much KiO3 is present. Correct? So you realize this is the chain of this is the flow that help you determine, right? So therefore you need to cover all three lah. Okay? So question is this. If I already have some thiosulfate present, then the question is how would it affect my burette reading? So if I already got some thiosulfate, so imagine initially I calculated I only need 26.3. But because there are some thiosulfate present, maybe now my thiosulfate required will be 26.00 because I already have some that is present and it will like maybe subtract some of the thiosulfate required. So you realize this one here means that there's a decrease. Okay, so my thiosulfate reading from my burette will decrease. That means I use lesser, right? Lesser thiosulfate. Lesser thiosulfate used. Lesser thiosulfate used will actually result in saying that there's lesser moles of I2, right? By saying that there's lesser moles of I2, this would mean that there's lesser KiO3 present. So know the chain of reaction, and then from there you can decipher. Some of you just say there's a change. They are not being specific enough. So you must be specific in this kind of question. You must tell me what is exactly the change that we are supposed to observe. Okay? So as you can see here, the amount of thiosulfate added from burette will decrease. Okay, because the conical flask already contains some thiosulfate. So this will result in the lower calculated number of moles of thiosulfate. This will mean that the number of moles of iodine will be lesser. This will mean that the number of potassium iodate will be lesser. So you must include this guy here and must include this guy here. You cannot, I say again, you cannot from the thiosulfate straight away jump to iodate. No. Okay, because you do not know what's the relationship between thiosulfate and potassium iodate 5 immediately. You need to go through how much iodine is present before you can go into how much potassium iodate is present. Okay, so this is for question 2. Okay, total 18 marks over here. Okay, question 3. This one is really a test of your QA. So this is a simple 3-mark QA. Okay, qualitative analysis. Now, this is the interesting part here. Many of you just do the experiment and never really think through, hey, actually, teacher, how should I go about writing it? How much detail should I include, right? What should I write? What was observation? This looks so different from what I normally do. But I want to tell you this, actually all your answers can be found in your data booklet. So what you have here, add a spatula X, clean, dry, add a piece of aluminium foil, sodium hydroxide. In your mind, once you see this, click, you know that this is a test for nitrate. This is a test for the anion, this is an anion test, but we're looking at very specifically as a test for nitrate. So your eye should straight away zoom into your observation, okay, to your data booklet, test for nitrate. What exactly should I see? Ammonia produced. Now, you know ammonia produced is not an observation. Okay, how do you know ammonia is produced? It's actually when you say that the damn red litmus paper turned blue. Isn't this something that I saw just now? Yes! Where do you see damn red litmus paper turn blue? Can you see this test for guess here? Damn red litmus paper turn blue. So a lot of the answers are already embedded within the QA data that's given to you already. Okay, but a lot of people never write some of you never write the word damn here. Okay, some of you got don't know what red, blue turn red. Wow, I'll tell you, big check as I see some of your writing because answers are already present. Okay, next thing, we are adding on a little extra element here that's not inside your data booklet, is that effervescence is observed. Okay, when you boil it up, initially some nature it's just boiling. But you realize that when you're heating it up, you're trying to activate the experiment. Okay, activate the whole reaction to start. Once it starts, right, you will see that there's a lot of effervescence occurring. You'll see effervescence occurring around the aluminum paper, around the aluminum foil. Okay, this actually, so when you're trying to heat it up, you're trying to activate the whole experiment. Once you activated it, you'll see that there's a lot of bubbling that's occurring at the around the aluminum foil itself. Okay, so We're looking for the effervescence plus the dam rate limit blue. That will be 1 mark, followed by ammonia is present because they ask you to identify the gas. So record your observations, identify the gas. So 1 mark here, 1 mark here. Okay, so there's the QA part. Next, to another portion of sample X, add about 4 cm3 of distilled water. Okay, so add this just to dissolve lah. This is just to dissolve. You can write down your result if you want. Okay, so dissolve to form a solution. In actual fact, you should write down dissolve to form a what color solution. Okay, the color, you should write it down, huh? But obviously in this question, we're not looking out so much for the color. The 1 mark is actually given to here. You only add aqueous sodium hydroxide. So this is actually a test for cation. You should be circling things like this and tell yourself, yeah, sure, test for cation. Okay, test for anion. Okay, so important. Okay, tell yourself what exactly are you doing? What's the test you are doing? Once you know the test, it's a lot easier because why? If I know it's a test for cation, okay, then tada, I can go and look at the thing, right? So all the answers for the test for cation is actually present here. So what you observe is that you saw white precipitate form. You add more sodium hydroxide, it doesn't dissolve. So how exactly should I express my answer? It's actually over here. You realize in the data booklet, the answer is still there. White precipitate formed. Okay, so you realize you must add a bit of your own words here. Insoluble in excess, sodium hydroxide. 1 mark. Okay, many of you don't know what to write, or you write weird stuff. Okay, take note, whenever you're doing QA, your data booklet is your best friend, okay? It will tell you what exactly you can write. But just take note, ammonia produced is not an observation, it's actually a conclusion. Not observation. You cannot see ammonia. Okay, what you can see is that the dam rate limits will turn blue. Okay, ammonia produced is actually a conclusion. So just take note. Okay, so this is for the 3 mark QA. Last one, planning. Potassium nitrate, potassium chloride are 2 salts. The energy change when they dissolve in water is endothermic. So whenever you see endothermic, you know that the temperature drop. Okay, when I put thermometer in, I should see the temperature drop. So just think. Plan an experiment to show which of these 2 salts produce a larger endothermic change per gram. Okay, because of the word per gram, I know I need to measure my mass. I want to know the larger endothermic change. Actually, I'm looking out for which salt causes a bigger, okay, temperature decrease. This is actually what we are looking out for. Okay, so I need to measure mass. I want a temperature, then I need my thermometer. Okay, and because I got water here, I need to measure my volume, right? Okay, so volume, most probably, you can use burette if you want. Okay, or you can use your measuring cylinder. It really depends on how accurate you want your answer to be lah. Okay, so I need to have mass, which I'll use my electronic balance. So these are the things you should be writing down as you are going through the question. Or you don't just read and you just straight away do. So ask yourself what are the things you need to measure, right? So I need to dissolve in water, so I make sure my volume is fixed, right? So I need to use different instrument measuring cylinder maybe to fix the volume. I want to measure change in temperature, so I need my thermometer. So I know another variable I need to think about is my temperature. Next one, I need to measure the change per gram, right? So I need the mass of the salts. So I need my electronic balance. Okay, and because this is a heat exchange, this is about energy change experiment. Typically, you will try to have an insulation. Okay, so that's why I'll think, maybe I should talk about how I can feed the whole thing into what we call a styrofoam cup, right? Okay, you have done an experiment like this before where you actually have it in a styrofoam cup. Okay, why? It's actually because you reduce the heat loss, right? Now, when you plan your experiment, you want to plan a successful one. So reduce heat loss is something you want to consider. So, yeah, provided with the potassium nitrate, ammonium chloride, and then a common apparatus. So you may include diagrams in your answer. Actually, in actual fact, you draw it, it may look easier for you to understand. But the word is you may. So if you don't want to include, it's also okay. So what we're going to do here is this. First, okay, I'm going to show you the whole answer here. So let's go through. First, I'll measure a fixed volume. Okay, how much we just read up to you, but the key idea here, we want a fixed volume of distilled water. Okay, what instrument are you using here? So I'm going to put all the instrument I'm going to use. So I'm going to use a measuring cylinder to measure the volume of my distilled water. Okay, what I'm going to do is, by precaution I'm going to take is I'm going to put it the precaution, why I say it's a precaution is because I want to reduce heat loss, right? So styrofoam cup is sort of like the additional layer to make my experiment more accurate. Okay, so once I put the water in, then I measure the initial temperature. I record it as T1. Okay, temperature, please take note, use a thermometer. So you just say measure temperature, then I ask you use what? Okay, so record it using a thermometer. Measure it as, and then record it as T1. Now, some of you say put the solid first, then you measure temperature. Normally when you measure temperature, you don't measure temperature of the solid, right? You measure temperature of the solution, the liquid. So start with the water first. Okay, so just take note. So measure temperature of the water. Okay, next I measure a fixed amount using an electronic balance and then measure as M1. Okay, all the data that you might be using later on. Okay, so actually this part here that I'm going to underline in, or maybe in light green. Okay, all this actually I added in later on. Okay, so I know that I want to measure temperature. Okay, now I'll just write measure temperature. I'll leave a space there because so maybe I will need it for calculation later. Maybe I don't need. So I'll just leave some space at the back. Okay, all this in green I actually added it on later on. Okay, so I say again, first thing I measure distilled water, add to styrofoam cup, measure temperature of the water, measure a fixed mass of my salt. Next, transfer in, and then stir the mixture. Okay, using your thermometer. The stirring part is just to make sure that it's evenly mixed. All my things have reacted. So you realize this is another precaution I'm taking to make sure that my experiment is as accurate as possible. Okay, once I stir finish it, I want to measure what we call the lowest temperature reached by the mixture. Okay, because I want to find which one is the sharpest drop, right? You realize I don't need a stopwatch here, because I'm not measuring the speed of which it reached the lowest temperature. I just want how much is the temperature change. So, measuring the lowest temperature reached by the mixture. Okay, this is another measurement. If you want to be kiasu, you can say temperature. I'm going to use a thermometer again. Okay, but in actual fact, you already say thermometer at the top when you're measuring temperature. So it's assumed that, yeah, you're going to measure temperature using thermometer. Okay, then once again, I put the T2 there. This is actually something that I added on later on. Okay, so I got the initial temperature. I got the lowest temperature reached, I got the volume of solution, I got the mass of the salt. So these are the data I actually obtained from my experiment. So then next, what's up, Cher? What should I do next? So because I want the endothermic change per gram, and I know endothermic change is related to temperature change, so I determine the change in temperature per gram. So what I did was, Cher, I need the change in temperature. So I'm going to use T2. So I'm going to assign the lowest temperature as T2. I'm going to assign the initial temperature as T1. So that's where I added those parts in green. I know I must have per gram, so I divided by the mass. So I determine the temperature change using this. Next, once I know the temperature change per gram for potassium nitrate, I will do the same thing for my ammonium chloride. So I'll repeat step 1 to step 6 with ammonium chloride instead of potassium nitrate. Because you must have the same conditions, right? You want to make sure that all your conditions remains the same. But now you're using a different salt. Once you have done that, I'm going to compare, okay, my temperature change per gram. The salt with the greater change in temperature. Now, greater change in temperature doesn't mean greater endothermic change. Okay, you must give that final conclusion saying that the greater change in temperature per gram means that it has a larger endothermic change per gram. So that's the final conclusion we are looking at. So your experiment must make sense. Okay, so exactly what are we looking for? I mean, these are the steps I run through with you to let you know the logic of the plan of the experiment. But how do we exactly go about marking? First thing, we're looking at your measurement must come with the apparatus. Do I have the sufficient measurements that I need? So temperature I need, volume I need, mass I need. And each of it must come with an appropriate instrument. So each of these measurements should come with the appropriate instrument that you need to use. Okay? Next, procedure and precaution. What we're looking out for is, are you taking note that this is a energy change experiment? Temperature, very sensitive. Hence, you want to minimize temperature loss. Therefore, styrofoam cup is important. Stirring the mixture well to make sure everything is reacted, also important. Okay, so we are placing a bit more emphasis on the procedure, the precaution part here. Next, So anyway, this one has to do with the approach of the experiment. Okay. So how do you go about doing the experiment, the procedure and the precautions required? Okay, to maximize accuracy. To maximize accuracy. Next, constant variable observed. So you repeat the same procedure with the other salt. So it's not just about doing, not just say, like add another salt. You need to say you repeat the procedure, the same procedure with the other salt. That's a constant variable observed, right? It's like doing experiment. Your constant variable is observed so that you can have a accurate comparison, reliable comparison. Okay? And lastly, once you've done that, we are looking at, you can conclude how do you know the energy change per gram? Actually, you are relating the endothermic change, the energy change per gram, to the temperature change per gram itself. So this is how you go about doing the planning for this. Okay, and I hope after going through this one experiment, you realize time is an important factor. You need to make sure that you are doing the thing promptly, but read your instructions carefully. Okay, read your instructions carefully, making sure you answer every single thing. Okay, so that's all for this.